Hey everyone, welcome to today's Explainer. I'm going to be your instructor as we step into a true physics masterclass today. We are going to demystify some of the most fascinating concepts in all of mechanics, specifically how we put massive objects into space and exactly what it takes to leave Earth behind entirely. So grab your notebooks because we're diving deep into the science of escape and orbital velocity. Let's just jump right in with a question that honestly trips up almost everyone at some point. If gravity is this constant force of attraction, always pulling objects toward the center of a planet, why don't the thousands of satellites currently floating above our heads just fall straight back down to Earth, right? It's a classic Socratic puzzle that kind of challenges our everyday intuition. And the answer? Well, it unlocks the entire foundation of orbital mechanics. Here's a quick look at our syllabus for today's masterclass. We'll start with gravity and motion basics, then orbital velocity, which is essentially continuous falling, followed by escape velocity for when we want to leave Earth entirely. After that, we'll hit the math behind the motion, bust some common physics myths, and wrap up with real-world space applications. Section 1. Gravity and motion basics. Before we start calculating how fast a rocket needs to go, we really need to understand the grand conductor of the cosmos, which is gravity. Gravity is simply the force of attraction between objects with mass. And this brings us to our first core definition, orbital velocity. This is the minimum horizontal speed needed for an object to continuously fall around a planet instead of falling onto its surface. Think about swinging a stone tied to the end of a string. That string is constantly pulling the stone inward toward your hand, just like gravity pulls a satellite toward Earth. But the stone keeps moving around you because of its forward speed. Together, that inward pull and that forward speed, they create an orbit. Now contrast that with escape velocity. This is the minimum speed an object must have to completely escape the gravitational attraction of a planet without using any additional propulsion once it hits that speed. Imagine throwing a baseball straight up. You throw it slowly, it falls right back down. You throw it faster, it goes higher. If you could somehow throw it at an impossibly high speed, ignoring air resistance obviously, it would literally break the tether of gravity and never come back. That critical threshold, that's escape velocity. This actually brings up a brilliant thought experiment devised by Sir Isaac Newton way back in 1687, known as Newton's cannonball. Imagine firing a cannonball from a really high mountain. You fire it slowly, it just falls back to Earth. You fire it a bit faster, it lands farther away. But if you fire it fast enough, the Earth curves away beneath the cannonball at the exact same rate that it falls. It continually falls around the curve. And if you fire it even faster than that, it escapes Earth's gravity entirely. Newton intuitively connected the simple act of throwing a rock with the complex mechanics of launching a spacecraft. Section 2. Orbital velocity, continuous fall. Let's look a little closer at the fascinating mechanics of how things actually stay up there. You know, it's fascinating to really look at the exact forces acting on an orbiting satellite. A lot of people think satellites float because there is no gravity in space. That is completely 100% false. Gravity is almost as strong in low Earth orbit as it is right here on the surface. The gravitational force pulling the satellite inward acts perfectly as the centripetal force required for circular motion. Because the satellite has this immense forward velocity, as it falls, the Earth simply curves away beneath it. It is literally in a continuous state of freefall. So the million-dollar question is, just how fast do you have to go to achieve this continuous freefall? Well, near Earth's surface, orbital velocity is approximately 7.9 kilometers per second. That is an absolutely breathtaking 28,400 kilometers per hour. That is the sheer speed you need just to stay in low Earth orbit without plummeting back to the ground. Section 3. Escape velocity, leaving Earth. Okay, but what if we don't just want to circle the Earth? What if we want to go to the Moon or Mars? Here, we have to shift our focus from staying in orbit to the immense energy required to climb completely out of Earth's gravitational well. To totally overcome Earth's gravitational binding energy, you have to hit this staggering number, 11.2 kilometers per second. That translates to over 40,000 kilometers per hour. If a spacecraft hits this speed, and again, assuming we ignore atmospheric drag, it will just keep moving farther and farther away into deep space, never to be pulled back to Earth's surface. I absolutely love using analogies to make physics click, and this one really hits the nail on the head. Imagine a deep, steep valley. Orbital velocity is kind of like riding a bicycle around the valley's circular path. You're moving fast enough to not fall into the center, but you are still trapped within the valley's walls. Escape velocity, on the other hand, is like pedaling fast enough to climb completely out of that valley and just leave it behind forever. One lets you stay inside safely, the other lets you break free. Section 4, the math behind motion. Now, don't let this next part intimidate you. As a physics teacher, I promise you, the math is just the cheat code for understanding the universe. Let's see what the variables actually mean. This reveals a seriously beautiful relationship between our two velocities. When you do the math, basically dividing the escape velocity formula by the orbital velocity formula, you get the square root of 2, which is approximately 1.414. What does that mean? It means that regardless of a planet's mass or its radius, escaping always requires exactly 41.4% more speed than orbiting. It is just this perfect, standard mathematical relationship baked right into the fabric of mechanics. Let's quickly summarize these core differences on our virtual chalkboard. Orbital velocity keeps you revolving at 7.9 kilometers per second around Earth, requiring lower energy. Escape velocity sends you away from Earth at 11.2 kilometers per second, requiring significantly higher energy. But look at the bottom row. Does it depend on the object's mass? No way. Because of the conservation of mechanical energy, the mass of the satellite or the spacecraft completely cancels out in the equations. A tiny 100-kilogram probe and a massive 10,000-kilogram space station require the exact same orbital speed at the same altitude. How cool is that? Section 5, Busting Common Physics Myths. Look, as an instructor, nothing makes me want to pull my hair out quite like the misconceptions that constantly trip up physics students. So let's clear up some of these cognitive traps. Let's just rapid fire through these. Myth number 1, gravity disappears in space. Reality, absolutely not. It extends infinitely, it just weakens with distance. Myth 2, rockets instantly hit 11.2 kilometers per second off the launch pad. Reality, modern rockets accelerate gradually using continuous engine thrust. That 11.2 number is the speed needed if no further propulsion is used at all. And myth 3, which we just touched on, heavier rockets need greater escape velocity. Reality, escape velocity depends only on the planet's mass and distance from its center, never ever the spacecraft's mass. Section 6, Real-World Space Applications. All right, let's bring all this theoretical physics back down to Earth for a minute and see how these fundamental laws power our modern world. Humanity's mastery of these equations has literally defined the space age. In 1957, Sputnik 1 became the first artificial object to achieve orbital velocity. In 1961, Yuri Gagarin proved humans could actually survive that continuous freefall. By 1969, Apollo 11 demonstrated an escape trajectory to leave Earth's immediate gravity to go to the moon. And in 1977, the Voyager missions pushed the limits even further, achieving the velocity needed to escape the solar system entirely. And today, we rely on these calculations literally every single minute. GPS satellites require perfectly maintained orbital velocities to give you accurate locations on your phone. Weather satellites use stable orbits to track hurricanes. The International Space Station completes an orbit every 90 minutes, flying at about 7.66 kilometers per second. Without mastering orbital and escape mechanics, checking your phone's map or forecasting the climate would simply be impossible. We've gone from simply trying to understand how an apple falls from a tree to calculating the exact mathematical threshold required to hurl a robotic probe completely outside of our solar system. As we continue to use these fundamental laws to push further into the cosmos, toward Mars, Jupiter, and way beyond, I want to leave you with this final thought. What new boundaries of physics will humanity need to escape next? Thank you so much for joining me for this Explainer Masterclass. Keep gazing at the stars, and as always, stay curious.